Get started. Thank you all for coming. I want to introduce our third speaker of the lecture series, the Compass Lecture Series, Kevin Langhoff. He did his undergrad studies at his home state at the University of Wisconsin. He's now a graduate student here at Berkeley Center for Theoretical Physics, and has worked on a variety of topics related to beyond the standard model physics, including dark matter, axions, and collider physics. So let's welcome our first speaker, Kevin.
Yeah, well, thank you very much for having me. And so today I'm going to, I have a pretty big task. What I would like to explain to you is our current understanding of essentially everything in the universe. So, it's a little bit challenging, but we'll see how it goes. So I'm going to be talking to you about the standard model and what we might believe lies beyond this particular model of nature. And it's all going to be from the perspective of theoretical physics, okay? But I'm going to talk a little bit about how it also relates to experiments. So first off, I would like to get started by actually asking you guys a question. What do you guys think about when I ask you, what is theoretical physics? What's the first thing that pops into your head? Okay, well, mathematical physics, yeah, good. So mathematics, that's a really important part, right? Does anyone else have any ideas? Yeah? Yeah, Albert Einstein. And, so this is what I hear quite often when I ask people, what they think about when they hear theoretical physics. They think of particular geniuses, right? Geniuses like Albert Einstein, Richard Feynman, Sheldon Cooper, these different people. And I actually think, this is not necessarily the best framework to have in mind when you're thinking about theoretical physics, because this notion of genius, it can be a little bit dangerous, right? And I know very few geniuses in theoretical physics. Really, all you need for theoretical physics is curiosity, right? Curiosity and determination to actually investigate the questions. And in particular, I think it's extremely important to constantly ask the question, why? I think this is the most important question in theoretical physics. Why does something happen? And so, to get an idea of how this works, I'd like to consider an example. And so first off, I have a question for you. I'm standing before you and I'm not falling through the floor, right? And why am I not falling through the floor? So can any of you give me an answer that you would have learned maybe in high school? Why do I not fall through the floor? Yeah, exactly. So, you normally draw a free body diagram around like a little box or something like that, or maybe even a dot. And then you draw normal force under gravitational force, and you say the, forces cancel, and therefore I don't fall through the floor, right? So that's, the answer we first learned. But then you can ask the question, why is there a normal force? Right? So why is there a normal force? Good, yeah. So the answer at the end of the day is electromagnetism. The atoms, which I'm made up of, and the atoms of the floor are repelling each other. And you can even discuss how this is related to, Fermi-Dirac statistics and Fermi exclusion principle, but that's not really necessary. The main idea is it's electromagnetism. But you can go even one step further. So you can ask, why? Why is there an electromagnetic force? Why do some charges repel other charges? And so why is that? Does anyone know? Sorry, what's that? Symmetries. Symmetries. Oh, that's actually a really deep answer. Yes. Yeah, symmetries. But maybe I'll take a more particle physics approach, as opposed to maybe a mathematical approach, and I'll say that there's an interaction through a photon. Okay. So this electromagnetic interaction is nothing more than the exchange of a photon. And the way that particle physicists think about electromagnetism is through diagrams like this. And so here on the x-axis, I'm showing essentially what is space, and on the y-axis, I'm showing time. And as the electrons approach each other, what happens to our current understanding of particle physics is that one of these electrons exchanges a photon, and it interacts with the other electron, and this is what fundamentally causes the repulsion between these electrons. Okay. And what you can learn from this is that in particle physics, forces actually correspond to particular particles. In this case, electromagnetism corresponds to a particle which we call the photon. This is actually responsible for light as well, right? Light consists of particles called photons. These diagrams are actually very deep, right? We take these very seriously. And the only rule when it comes to these diagrams is that, for electromagnetism at least, is you have to have two electrons connecting up with one photon. And any diagram you draw, as long as it obeys that principle, will be a possible interaction in nature. Yeah. Essentially, yes. I mean, but this is a quantum mechanical process. But yes, the electromagnetism, there's constantly photons which are being imparted upon each other. That's correct, yeah. Good. Okay, so as I was saying, the only rule is that two fermions, two electrons, have to interact with one photon, right? There's a particular vertex here. By vertex, I mean just a connection. And I can also draw a diagram which looks like this, right? As long as I'm obeying the rules, which I am. And what we learned from this diagram here is actually something that's also quite interesting. So initially, at the bottom of this plot, I have a positron electron, and both of these have mass. And at the final state of this system, I have two photons, and photons are massless, right? So what happens here is that mass is converted into energy. And so in other words, this is just a representation of E equals mc squared. Mass is just a form of energy, and it can be converted into different forms of energy. Okay. But that's just an example. And so now I want to get into what I really care about as a theoretical physicist, which are the fundamental laws of nature. Okay, so what are the fundamental laws of nature which describe everything that we see around us? And so really this involves some of the biggest questions we can possibly ask. So for example, what is everything made of? Right, this is a very big question. As well as what laws, actual physical laws, govern the way in which these things interact. And what is the universe? How did it form? And how will it evolve as time goes forward? So it's quite ambitious, right? These are very big questions. And we actually have an answer, and it's a mathematical answer at the moment. Everything that we currently understand about the universe can be explained with this equation here. And I don't expect you to understand this equation. But look at the beauty of this thing. It's so simple, right? And in some sense, if you unpack this equation, it describes every single thing we see around us, which is really remarkable. Not just the particles and their interactions, but also gravity, and the quantum mechanical nature of all of that. Okay, yeah. Yeah, so this includes gravity and quantum mechanics. There is general relativity in this expression. There's also quantum mechanics. And here we have a quantum mechanical theory of gravity. It is not a complete quantum mechanical theory of gravity because it will break down. And I'll actually discuss this in a moment, why it breaks down. So, this doesn't describe everything that we observe. There are many things that we observe that we cannot explain with this equation. And this is mostly what I'll be talking about today. But this is our current understanding of the universe. Okay, but what I want to focus on at the moment is what is everything made of? And to do this, I'm going to just zoom in as far as we possibly can to matter. Okay, so what we learned in high school is that everything consists of atoms, right? And atoms consist of nuclei, which are they have different amount of protons and neutrons, and electrons, which orbit around them. But in quantum mechanics, it's more like a wave or a cloud of electrons. But these are the constituents of an atom. But you can zoom in even further. So you can zoom in to the nucleus and into the protons and neutrons, and you will find that the protons and neutrons actually have constituent particles. So they're made up of things called quarks. Okay? So each proton and a neutron is made up of roughly, you can say, 3 quarks. And there's a much more precise description of this, which I won't go into. But this is the idea. Okay. And furthermore, these quarks interact through a force called the strong force, which again is described by a particular particle, in this case, the gluon. All right. So that's our second force that we're describing. So we talked about electromagnetism, and the particle which corresponds to that force, which is the photon. Here we have the strong force, and the particle which corresponds to that is called the gluon. Now, you might also ask the question, why not zoom into an electron? Why not zoom into an electron? The electron must be made of something too, right? If protons and neutrons are, why not the electron? And, you can, but what you'll find, at least, what we've currently found, is that an electron seems to be a fundamental particle. Doesn't have to be. There might be, some better description of electron that we find later on, but right now it's a fundamental particle. So there's some processes that can't be explained with the electromagnetism or the strong force, one of which is neutron decay, okay? So if I have a neutron, sometimes it will decay, and it will decay into a proton and an electron, but also another particle, which we call a neutrino. And this is a very light fermion, which has no charge, okay? And much later on, we found out that this interaction is actually mediated by another force called the weak force. And the particle which corresponds to the weak force, at least for this process, is called the W boson, okay? So now we've learned all three forces, the electromagnetism, the strong force, and the weak force. These are all the forces we know of nature, but there's actually one more property which is really important, and that's the Higgs field, okay? So what is the Higgs field? Well, the Higgs field is a field that exists everywhere in nature, and it has a particular, essentially value, it's like a fluid that's everywhere in nature, and some particles will pass right through it. They won't even notice it. So photons will pass right through the Higgs field. It will interact not at all with the Higgs field. But some particles, like the electron, will actually interact with the Higgs field. So you can kind of think of this as, forming I don't know what you would call that, like a dent in the Higgs field. And this dent in the Higgs field gives the electron energy, which we call mass, okay? So this is how the Higgs field gives mass to particular fundamental particles, like electrons. And different particles interact more strongly with the Higgs field. For example, a muon, which looks like an electron in essentially every way, except for the fact that it interacts more strongly with the Higgs field and therefore has a larger mass, okay? And so now we've learned about, essentially all the fundamental interactions of nature. And I can just give you the answer of what we believe our, everything is made of. And this is it. This is the table of all the fundamental particles that we're aware of. And so let me break this down a little bit. So, first off, as we were discussing, you have the up quark, the down quark, and the electron, and these make up the proton, the neutron, and, also the electron, right? And this describes everything that we see on a day-to-day basis. But once you start talking about what you actually see, then, what you actually see is actually a photon, right? That's what you see at the end of the day. That's what light is. So these are the particles that we care about on a day-to-day basis. But there's more particles, and in particular, for all the fermions that I was previously describing, the electron, the quarks, and the neutrino, for some reason, a complete mystery to all of us, there's actually 3 generations of these fermions. They're just copies. They're copies, but they have different masses. Nobody knows why this is. But all the heavier particles, they'll decay to the lighter particles, and so we don't actually see them unless we produce them somehow. Furthermore, these fermions can be broken up into essentially 2 categories. One category is the quarks. The quarks interact through the strong force. That's what defines them. The leptons are defined as the particles which don't interact through the strong force. Okay, so that's like the electrons and neutrinos. And we also have the force carriers, also called gauge bosons, and these are closely related to symmetries, as you mentioned before. And so these describe the forces that we see in nature, as well as the Higgs. Okay, and again, this gives mass to all the fundamental particles, or most of the fundamental particles, because it actually only gives mass to these particles here that are highlighted, okay? And if you look on this plot on the bottom right, which shows the mass of all these fundamental particles in units called giga-electron volts, and this is just a unit for mass, if you want. And if you want a reference, a proton has a mass of 1 giga-electron volt. So here are all the masses of the fundamental particles. And the Higgs gives a mass to all the particles shown in this yellow box. I've also shown on this plot the masses of the neutrinos, right? And this is a complete mystery. We know, at least fairly well, the masses of some of these neutrinos. Okay, we know they're non-zero, and we don't know why. We have absolutely no idea why. It might be related to the Higgs field still, but it might also be related to something else. Okay, but how do we actually study these particles? Right now, I've given you, everything that we know, but how do we actually find out information about these particles? And the answer is colliders. Okay, colliders are, they're our telescope into the most smallest length scales. Okay, to learn about these particles. So how do colliders work? Colliders work essentially through this equation, E equals mc squared. Okay, so what does E equals mc squared mean? It means I can convert energy into mass or mass into energy. And for a collider, we usually convert energy into mass. So here's an example of a collision of a positron and an electron. And if they have high enough energy, they can produce heavy particles, particles with a large mass. So this is how we can actually study these heavy particles. But once we produce these particles, we can't just like bring them into a lab and then take a look at them with a microscope, because they decay very quickly. Some of these particles decay in time scales that are smaller than 10 to the minus 20 seconds. So you'll simply never see them. But what you will see is their decay products. And these are the particles through which we actually learn about these heavy particles. Okay. And colliders have been very successful for discoveries of fundamental particles. So here on the left, I'm showing a plot of the center mass energies of various different colliders, which collide electrons and positrons for the blue dots, and protons or hadrons in the red dots. And on the right, I'm showing the mass of the fundamental particles versus the time at which they were discovered, the year in which they were discovered. Okay. And what you see is there's a very clear correlation between these two plots. You can actually just translate one of these plots to the left, and you see, so here I'm pointing to the collider at which these particles were discovered, and you can pretty clearly see the correlation. I would like to briefly consider the collider on the very top right of the left plot, the LHC. Okay, and this stands for the Large Hadron Collider. And so this is currently our highest energy collider that we have ever built. And it's located in Geneva, Switzerland, and it's roughly 27 kilometers in circumference. And to give you a reference of how big that is, I've overlaid the size of this collider in the Bay. Right? So it almost takes up the whole, Berkeley, San Francisco Bay Area. Pretty big collider. Okay. And, in order to see the particles which are produced, we need a detector, right? To detect the products of the decay of these particles. And this is one of the detectors called Atlas. And it consists of many different components. It's very complicated. If you can see, there's people down here on this yellow platform to give you a comparison for the size of these objects. It's massive. And the events of the collisions will be very complicated in these detectors. We'll be able to reconstruct that event in order to learn about the fundamental particles. And the LHC has been extremely successful. Okay, so the LHC has discovered the Higgs in 2012, and here's a plot of the process which discovered the Higgs. So the Higgs was produced, and then it decayed into 2 photons, and the photons were measured, and if you reconstruct their mass, you'll find a little bump, and that bump corresponds to the photons produced from the Higgs decay. So this is how we discovered the Higgs, and in some sense, this completed the standard model. This was the last particle predicted to exist within the standard model of particle physics. Okay, but the LHC didn't stop there. It's been very successful in many other ways. So here I'm showing a very complicated plot, but all you need to know from this is a bunch of different standard model processes, different collisions which occurred. And what I'm showing here is the comparison between the experimentally observed results versus the theoretically predicted results. So the theory is in gray, if you can see, and the experimental results are the colored dots. And essentially they all overlap. It's remarkable. It's really remarkable. The standard model is incredibly predictive, incredibly successful. And it works very, very well. It makes all these predictions extremely precisely and accurately, but really that's the problem. The problem is that it works too well. It works too well for the simple reason that there's many things that we cannot explain with the standard model. So there must be something else. There's many problems, like the ones I show here, which need something more to get a proper solution. So, let me elaborate a little bit more on some of these problems. So, first off, I was talking about these masses of these fundamental particles, the ones which get their mass from the Higgs. And, if you look at this for a while, it's very confusing, right? But there does seem to be some structure there, right? But nobody knows how to explain the structure. It's a complete mystery. And just like how the periodic table, right? The periodic table had some structure, and there was an explanation for that in terms of atoms. It would be wonderful if we could get an explanation for the structure of these masses in terms of some more fundamental theory. Additionally, as I said, yeah. So that's what we currently do.
Repeat the question.
Yes. So the question was, can you actually predict the strength with which each particle interact with the Higgs? And the answer is actually, in some sense, no. Because you cannot actually predict the strength of these fermions. That's what we're looking for. We're looking for that answer. Can you actually do that? Is there some model through which you can do that? And at the moment, the answer is no. We don't have a model which predicts these masses. That's not possible. But that would be the goal. Yeah. So what I mean is, so if you look at the masses of these particles in the yellow box, so they have all very different masses. In fact, it spans 6 orders of magnitude. The top quark is about a factor of 1,000,000 heavier than the electron. Why? Right? No one knows. No one has any idea, right? That's the mystery of this. And neutrinos are even much, much lighter, right? Significantly lighter. And nobody knows why. It's a complete mystery. Okay. Furthermore, the matter which makes up the universe that consists of standard model particles, protons, neutrons, electrons, that only makes up 5% of the energy that we see in the universe. The other 95% of energy consists of dark matter and dark energy, which we don't understand at all. Okay. So that's something that also needs an explanation beyond the standard model. Finally, as you were mentioning before, we don't have a good theory of quantum gravity. We can quantize gravity, but it will break down. And so that's actually the first thing that I want to discuss, because this will be the thread which unravels the standard model and will point to important ways to search for new physics, okay? So let's actually start with quantum gravity. So why is quantum gravity bad? So first off, you can quantize gravity. There's nothing wrong with that. There's a mathematical procedure to do so. And the particle which corresponds to the gravitational force is called the graviton. And you can reproduce Newton's law of gravity through this graviton. But quantum mechanics throws a wrench into things. And it does so in the following way. So gravitons can actually split into 2 gravitons, reconnect, and then interact back with the electron like this, okay? In other words, we're popping a graviton pair out of the vacuum, okay? In a quantum mechanical way. There's a very mathematically precise way to do this, but at the end of the day, what happens is you get a correction to Newton's law of gravity. And the correction is the following. And, you might say, well, we must have seen this at this point, right? There's a correction, but we haven't. And the reason why is because this correction only becomes sizable at length scales smaller than 10 to the minus 35 meters. And you're never going to see that in a lab, right? That's never going to be observable. And you might say, well, then I don't care. Well, that you can care because this means your theory doesn't work at some point, right? And there are some systems that it matters. For example, black holes, okay? So if you take Einstein's theory of gravity very seriously, then at the center of a black hole, you have a singularity where the curvature of space-time is so strong that your quantum theory of gravity breaks down, okay? So we cannot understand the center of black holes with our current theory of gravity. Furthermore, if you retrace the history of the universe back to its beginning, you'll find that there is a moment where the universe was so highly curved that also gravity breaks down. So we can't understand either of these two, deep questions with our current theory of gravity. And so at the end of the day, what this means is that we need some new physics to show up at a particular length scale, 10 to the minus 35 meters, or equivalently, I can convert this into a mass scale, and that's about 10 to the 18 giga electron volts, okay? So, one possible theory for this is string theory, but I won't go into that. Okay. So why does this matter for particle physics? It matters because of the Higgs mass. And so, if I show you this plot for the masses again, you might say, well, there's nothing weird with the Higgs mass. It seems pretty normal compared to all the other particles, right? But there's actually a problem with the Higgs mass. And the problem is related to the fact that we expect new physics to show up at higher masses or higher energies, okay? And once you assume there's new physics at higher energies, the Higgs mass becomes very weird. And it becomes weird because you expect the Higgs mass to receive corrections from quantum mechanics, which will pull the Higgs mass up to that new physics scale, okay? And if new physics shows up at 10 to the 18 GeV, you'd expect the Higgs boson to be much, much heavier than it currently is. So why is it not? That's the big question. One solution to this question is let's just cut the spring. Let's cut the connection which pulls the Higgs up to higher masses. And this solution has a name. It's called supersymmetry. Okay. And before I go into supersymmetry, I want to give you a warning. Supersymmetry is just a theory. Okay. It's just a theory at the moment. No one's discovered supersymmetric particles. And in fact, the LHC has constrained the model space of supersymmetry quite a bit. So supersymmetry may not be how the universe decided to exist. But we don't know that at the moment, and it's still very well motivated, extremely well motivated, so it's still worth investigating. There are other solutions to this problem. Actually, can anyone tell me another solution to this problem that maybe you can see just from this picture? So I can either cut the spring. What else could I do? Fix this problem. Sorry about that?
Another type of Higgs boson? Maybe there's three.
Yeah, maybe there's three. I don't know if that would fix this problem. But one way that you could fix this problem is to bring that purple dot to the left, right? Bring it all the way, very close to the Higgs mass, and then you don't really have a problem anymore. This is, in fact, what models of extra dimensions of space do. So there are some, serious models where you add additional dimensions, and this will explain the Higgs hierarchy problem, the Higgs mass. Okay, but let's talk about supersymmetry, and before that, let's talk about symmetry. So I think, yeah. Oh, that's a great question. Yeah, so the question was, so in this slide, I showed 10 to the minus 35 meters, but then I also said that, in some sense, this is equivalent to a mass scale of 10 to the 18 giga electron volts. And the reason why we can do that conversion, even though, length is definitely not mass, right, is because h bar, the Planck's constant, and c, the speed of light, are considered to be fundamental constants. Okay, and so, for example, c will convert times into lengths, right? When we talk about light years, right, that's a time in some, well, light years is a distance, right? But we're converting year into a distance, right? And you can, when you have h bar and c, you can convert lengths into masses. So that's how I made that conversion. Yeah. Great question. Okay, so before I talk about supersymmetry, let's just first talk about symmetries, as you already brought up. So symmetries are a very deep part of describing the universe in which we live in, and we all have a notion of symmetry built in, intuitively to us. And so we would all take a look at this picture, and we'd say, well, this is a very symmetric picture, right? So what are some of the symmetries of this picture that you can point out? And I haven't even defined symmetry, but right, I think you all have an intuition for what symmetry is. So why would you say this is a symmetric picture? What's that? Good, yeah. So the main idea is that this picture is invariant under certain transformations. So some of those transformations are translation. If I take this picture and I move it in a very specific way, it will look exactly the same. Okay. Furthermore, I can actually do a rotation, and again, it will look the same if I rotate about the right point by the right angle. And finally, I can also do a reflection, as you say, and the picture will look the same. Okay, so these are some examples of symmetries, and it turns out that the laws of nature obey certain symmetries. So one symmetry that exists in the laws of nature is that if I perform an experiment in a lab, it doesn't matter if my experiment is oriented like this or like this, I should get the same physical result. Okay, I should observe the same laws of nature. For example, if I have two masses that are oriented like this, they'll attract each other with the exact same force as two masses which are oriented like this. Okay, so we say that there is a rotational symmetry of nature. But of course, any of you would say, well, this is ridiculous, right? If I'm standing in this room, certainly, there's one direction which is very special. It's up and down, right? If I throw a ball, the ball goes down. It doesn't, fly over there. So symmetry is broken on Earth, and it's broken because of the existence of the Earth. The laws of gravity still are rotationally symmetric, but because of the existence of the Earth, that symmetry is broken in some sense. That doesn't mean that the laws are broken. The rotational symmetry, the laws of nature are broken, just means because of the special place that we live in, some of that symmetry is broken. Okay. But of course, for this example, some symmetry remains. So it doesn't matter if I shoot a cannonball in one of these directions, it'll look. All that matters is the angle. Okay. Furthermore, there's another important thing about symmetries is that symmetries may evolve with the temperature of the universe. And we're actually very familiar with this because of the existence of magnets. So at very high temperatures, the spins of the electrons within magnets are pointing in all different directions, completely randomly. And so there's no one special direction inside of a magnet at very high temperatures. But as I cool the magnet, the spins, at least for a ferromagnet, will eventually align in one particular direction. And so now there's one direction which is specified or special, right? And so the symmetry, which previously existed, the rotational symmetry that no direction is special, has broken. And so this may also be how our universe is. In fact, it probably is. Okay. So what is supersymmetry? Supersymmetry is just asymmetry of the laws of nature, and it is this symmetry. So for every fermion, spin 1/2 particle that I have in the standard model, supersymmetry says that there exists a boson, a spin, in this case, 0 particle, a scalar particle. So, for example, for the electron, there would be a scalar particle called the selectron, and if the symmetry were exact, the selectron would have exactly the same mass and interactions as the electron. Okay, so that's what supersymmetry would suggest. Exact same thing with the gauge bosons. The gauge bosons, which mediate forces. So they were originally spin 1 particles, and in supersymmetry they will have a supersymmetric partner called a gaugino. I don't know who came up with these names, which is a spin 1/2 particle, a fermion. Okay. It turns out that in supersymmetry, you also require two Higgs bosons, but that's a detail that I won't really get into. But why is this symmetry special? So it's special and it's motivated by many different reasons that I'm not discussing now, but in the context of the Higgs mass, it's special for the following reason. So, I won't go into the reason why these diagrams correspond to corrections in the Higgs mass, but here they are, okay? So these diagrams are what gives us corrections to the Higgs mass. And the Higgs mass will receive corrections proportional to the mass of the particles showing up in these loops, okay? And supersymmetry says that for every fermion loop, I will have a boson loop with exactly the opposite contribution to the Higgs mass, okay? And what this means is that the total contribution to the total correction to the Higgs mass is 0. There's no large corrections to the Higgs mass. And so this essentially cuts that spring, which pulls the Higgs mass up to higher energy scales. Okay. So, there's math that goes into this and it's a little complicated, but this is the main idea. Yeah.
About antiparticles.
Antiparticles, they still exist in here. So for example, electron showing up in a fermion loop would also have a positron. But that's that isn't related to the supersymmetry.
So for example, if the electron and anti-electron, they are fermions, but if according to supersymmetric theory, they have boson in the supersymmetric part, but boson has no antiparticle, or the antiparticle is
But they do, because they're complex scalars.
so they are conjugate.
Yeah,
Oh.
yeah, exactly. Yeah.
What are the electrons of these extra particles?
Oh, well, so these particles actually are they're virtual particles. So they're never really existing in nature. They're essentially popping in and out of the vacuum, and they only exist due to the Heisenberg uncertainty principle. So they're only existing for a very short period of time. Yeah, but they don't really have a particular lifetime per se. Does that make sense? It probably doesn't. Like it's a weird thing, right? And I don't know if I can give a very good explanation for it. Virtual particles are a little funny. Yeah. So the contribution to the Higgs mass from fermions, the correction, is opposite of the correction from bosons. Yeah. Okay. But Susie's actually broken, and I'll go through this a little quicker. That's not super important, but since Susie's broken, and we know it's broken because we don't see a scalar electron with the exact same mass as the electron. So Susie has to be broken, and this actually predicts, or how should I say? So the observed mass of the Higgs actually predicts the scale at which we expect these supersymmetric particles to show up. Okay. And so here's a plot from one particular paper, which shows the mass of the supersymmetric partner of the stop quark as a function of one of the supersymmetric parameters, model parameters. And what you see is that it's actually always a little bit heavier than what is observed at the LHC, or the constraints from the LHC. And this may be very similar to what happened at LEP. So at LEP, we actually stopped running at an energy of 209 GeV, and this was actually just out of reach of observing the Higgs. So this was a collider which existed before the Higgs was discovered. It was looking for the Higgs, and it stopped right before it could have observed the Higgs. Bit of a shame, but this may be the case with the LHC as well. So Susie's broken. It predicts a scale at which we expect supersymmetric particles to show up, and these may be potentially accessible at a future collider. Okay, but future colliders cost billions of dollars. Okay, so which one should we build, right? There's many different proposals for future colliders. Which one should we build? And this is really like being at an ice cream store, right? There's many different choices of ice cream that we could potentially pick. They all have different, flavors, right? But we can only pick one. That's what our mom says. Our mom is government. So which one should we pick? And there's many different choices. So the choices correspond to which particles you want to collide. So if you want to collide electrons, you also have to choose a shape of your collider. If you want a circular collider, there's two options. There's the FCC, the Future Circular Collider, as well as the CEPC, which corresponds to the Circular Electron-Positron Collider. You could also have a linear collider, and there's many different choices for that. And then finally, there's also a proton collider, okay? And these are just extensions of the electron collider. So there would be the next step. And another really interesting possibility is you can also collide muons. So this is very exciting. This is a very futuristic proposal, and it would revolutionize particle physics. We would be able to explore new theories well beyond our current capabilities. But there's a lot of technical challenges which go into the making of a muon collider. But it's very exciting. But I'm actually not going to focus on that. I'm going to focus on the circular electron-positron collider. And there's two proposals for a circular electron-positron collider, one of which is the Future Circular Collider at CERN in Geneva, Switzerland. And that could potentially start running in 2045 for the cost of $16 billion. Very futuristic, quite a bit of money, but very exciting. There's also another proposal in China called the Circular Electron-Positron Collider, which would be essentially the same, and it could run 10 years before the FCC for a third of the price. Also very exciting. And whichever one gets built, if any of them get built, that's fantastic for physics. So we'll see. But just to give you a reference of the size of these colliders, this is the LHC. This is the FCC. It's 100 kilometers in circumference. It's massive. And it's really, really interesting. It revolutionized physics. And it's a little bit different than the Large Hadron Collider, because the Large Hadron Collider, you just take two protons, you smash them together at the highest energy possible, and you hope that something interesting comes out. That's what a proton collider is. With an electron-positron collider, what you're actually doing is you're creating a factory for standard model particles, where you're trying to produce as many standard model particles as you possibly can, interesting standard model particles. For example, the Z boson, or the W boson, or the Higgs, or also the top quark. So the FCC or the CPC will run in stages where they produce these different particles. And you can produce a lot of these particles. So for example, the Z-pole run of the FCC, when you're trying to produce Z bosons, could potentially produce 5 trillion Z bosons. And to give you an idea of how revolutionary this is a factor of 100,000 more than was produced at the previous electron-positron collider. So, that'd be wonderful. And how could you actually see new physics in such, with such a Z factory, with 5 trillion Z bosons? Well, one possibility is the following. So what might happen is these SUSY particles might show up in loops in the decay of a Z boson. And it would correspond to the diagram shown on the right. And if you calculate the correction to the decay rates of the Z boson from this effect, you'll find the following result at a very qualitative level. So you get a mathematical expression that's not really important, but what's important is the equation on the right-hand side, which says that the masses of supersymmetric particles that you can actually explore with 5 trillion Z bosons is at the TeV scale, which is roughly comparable to the LHC. In fact, sometimes it's even better than the LHC. So this is one of the plots from one of my recent papers where I was looking into this. And I'll just bring your attention to a couple lines. So the yellow line on both the left and right-hand side plot, so the left and right-hand plot are just different models, different supersymmetric models. And the yellow line is the region of parameter space, which the FCC, 5 trillion Z bosons, could potentially exclude, okay? And the gray region is the region which is excluded by the LHC. So, there's lots of room for improvement, and the FCC is quite exciting for this reason. Okay, but what is the future? What is the future of particle physics? So the future of particle physics is uncertain. I think that's the best description I can give. There's lots of big ideas: supersymmetry, grand unified theories, extra dimensions, composite Higgs. But none of these grand ideas have to exist in nature. Nature does not care about how beautiful we think these different theories are. But there's hope. There's hope, and the reason why there's hope is there's incredible technology being produced by our experimental colleagues, and it's just very exciting. The new colliders, which could be created in the next couple decades, would revolutionize physics. And so, in particular for SUSY, Einstein was once asked, "What would you have thought if nature did not follow your law of gravity?" Einstein's law of gravity. And he would have said, "I would have thought that the Lord had missed a most marvelous opportunity." And I think that would be the case with supersymmetry as well, but at the same time, they don't really care, right? And we may have to rethink the assumptions that go into our explorations into particle physics. Maybe thinking about the Higgs boson and the corrections to its mass is maybe the wrong idea. Maybe we need to think more about the fermion mass structure. Maybe we need to think more about something else that we haven't even thought about yet. And this brings me to another important point. We need new ideas, and that may come from very creative young people such as you guys. And so now it's your turn to do interesting physics. And that's all I have to say.
So you said like photons are exchanged between particles when they experience the field. Can these photons be detected? Like, could I see that light or what?
Ah.
Concept?
So yeah, so let me go back to the figure. So at the very beginning, I was talking about how particle physics actually views electromagnetism. And I said that the electromagnetic force actually corresponds to two particles interacting through essentially like throwing a photon between them, right? No, you will never observe this photon. You can observe photons produced from these collisions, but you'll never observe this. And that's actually for a very simple reason, if you understand quantum mechanics. So when we're learning about quantum mechanics, we learn about this double slit experiment, right? And so we say, let's say we shoot electrons through two slits, and then we observe their impact on a wall on the far side. Well, if we're observing just the impact on the wall on the far side, we'll never actually measure which of the two slits it goes through, right? And if you were to measure which of the two slits it went through, the measurement would be completely messed up on the other side of the wall, right? And it's essentially that same principle. This photon is kind of like the two slits. So it's a quantum mechanical process. So no, you'll never observe this photon. It's not like an actual ball. Like I think in introductory physics, we talk about two ice skaters coming together and then we throw, a bowling ball from one person to the other. It's not like that. It's a quantum mechanical process. Hey, how's it going?
I have two questions. I was wondering why why is China's particle accelerator that does the same thing like a lot cheaper? Number two, what's controversial about the neutrinos? I hear that.
Ooh, controversial.
Questions about new physics there.
Okay, well, first, let me describe the neutrinos, because that's a simple question. So it's mysterious for a very simple reason, and that's that we don't understand it. So neutrinos have a mass. This must be the case because we observe oscillations between the different types of neutrinos. Just as they float through space, they oscillate between different neutrinos. And this is only possible if neutrinos have a mass. But we have no idea whatsoever how the neutrinos obtain that mass. We have theories. So one theory is that there exists something called a grand unified theory. And in this grand unified theory, there are additional neutrinos, which, through a process called the seesaw mechanism, give these standard model neutrinos a very small mass. But, they're just theories because we haven't observed any other big neutrinos. Okay, and then for the more complicated question, so, why is the circular electron-positron collider in China so much cheaper and can be built so much quicker? I think just because they, are better at building these things. Also, if you want to build something in Geneva, well, Geneva is a very expensive place, and you can't just dig a hole in Geneva and everyone's fine with it. But where they're planning to build this in China, I think the government is.
I'm from China, so for CEPC, two reasons why the CEPC is cheaper. The main reason is that the labor force is cheaper in China. That is acknowledged by the leader of CEPC. He said in that also, everything built in China is much cheaper than Euro in the USA. One is because of the labor force is cheaper. And another reason is this budget, $5 billion USD, it does not include many money for the labor force. So that's a trick. Yeah, so that's a trick for this budget number.
Oh, I see. Okay. Oh, nice. Thank you. Thank you. Yeah. All right.
Other question? Well, let's think our speaker one last time.
Thank you.